So the next thing that we discuss is leading up to the definition of essentially an isomorphism. And we start with the idea of an embedding, and this is on structures. So a structure M is embedded into a structure N if there exists a map eta, which we call the embedding. So eta is the embedding, and it is a map from structure M to N such that the map is one-to-one and preserves interpretations. Now, what I mean by the fact that it preserves interpretations, I'm not going to state fully. Hopefully, it's kind of familiar to other math classes that, the notion that an isomorphism in an algebra is, or a group is one which, if you perform the operation before mapping, it's the same as if you perform the operation after a mapping. So there will be a similar idea here. Now I'll spell it out for the case of a function. So if we have a function symbol in our set of function symbols, and a collection of elements out of the domain, enough of them so that we can plug in for all of the arguments of that function symbol, then to preserve the interpretation, it means that mapping that element, which the function itself, so to speak, maps within the domain, right? So here I get the function denoted by the symbol. I plug in all of its arguments with these particular arguments, and that gets me another element out of the domain of the structure M, and then I map using eta. So again, maybe it stands to repeat that eta is a mapping from the domain of M to the domain of N. So I get here an element out of the domain of M by this function denoted by f, and then I map that using eta. I map it over to the domain of N. Now, for eta to be an isomorphism, it must be the case, or an embedding, it must be the case that I could have mapped the individual elements first, and then used the... Oh, I have a typo here. So, I must it must get me the same thing as if I map the elements of the domain first, and then plug them into the denotation of the function symbol in N. So that in a sense, kind of like with a group, performing the operation, so to speak, before mapping gets you the same thing as if you mapped the elements first and then performed the operation in the sort of codomain structure. So that's the notion of an l-embedding, and if the function eta is in fact a bijection, then we call it an isomorphism. If in fact the domain of M is a subset of the domain of N, we call M a substructure. We could also say that N extends M. And this is just so much vocabulary. We also define the notion of a structure being infinite if the cardinality of the universe or domain is infinite. And so we'll continue with definitions in the next video.